Okay, so you have a line like this. And what did your second line look like relative to that? Steeper, less steep?
Less steep.
Okay, so something like this. Okay. Another group that had position independent, but their lines looked different than this. Mitch, what did yours look like?
Ours was about 0.3 meters.
So about here.
Yeah.
Okay. So what did your second line look like?
It was the same as line number 2, except it started at a different point.
Did it start here as well?
Yeah.
Okay. So it just slid along.
Yeah.
Okay. Any negative slopes that we had position independent? No negative slopes? You had a negative slope? Okay. So you started up here and went like that? Okay. How about your other line? So this is line number 1. What did, okay, so it ended at the same place, but it was a steeper line?
Yeah.
Okay, so
Good God.
starting where? So about 0?
Yeah.
Okay, so number 1 like that.
Yeah, number 2 was also positive, but last year.
So steeper line?
Yeah.
Okay.
Steep, but
Okay, so
Yeah,
like
that.
that maybe? And what did your other line look like? So it started down here? Okay, but at 0 or just a little bit lower than this one?
Little lower than that one.
Okay, so here, and it was steeper?
Yeah.
So like that? Okay, so that, like so. Yes? Something like that? Okay. So we got some interesting lines. That was a plan. One of the things when we have graphs, we need to find line equations. So, Allison, which did you have for independent, position or time? Okay, so we're over here. So let's come up with a line equation for this. Start me out, please. And we'll do it for an orange line, all right, because those go to 0. How would I start it? T sounds good, equals, what did you have for numerical slope? Whatever you had, I don't care which slope value you give me. One of your lines, 2.145. Okay, we'll wait on units for a minute. Horizontal variable. What did we say last week we were going to use for variable for position? All right, Chris says x. That's right. Plus or minus, Allison?
Minus.
Okay. Minus what? Go 3 sig figs 511. And what unit should I put for this? Well, that's my y-intercept, correct? So my units for y-intercept are good. So my slope, Brad, I got seconds here. I got centimeters here. What should I put for units for my slope? Seconds per centimeter. All right. That sounds good. Mitch, which vehicle's faster for the orange one, 1 or 2? So you say 2 is faster? All right. Hunter, do you agree? He says 2 is faster for the orange than 1.
yes.
Yes?
Yes.
But the slope's small. How can it be faster? Okay, so this one you're saying is faster because it takes less time, less seconds per centimeter to cover a certain distance.
Yes.
All right. Is that intuitively obvious when you look at the graph that the lower slope line is faster? Or do you have to think about it a little bit? Let's take a look at these. Let's do the blue lines here. Who had time as their independent variable? Joe, give us a line equation for a blue line. How do I start that out, sir? X is the variable we use for position. So X equals, did you have time independent, Joe? Did you have lines that kind of look like the blue ones?
Yes, I did.
So give me a slope value for one of your lines. So 44.007, you said?
44.40 centimeters per second.
So 44.4. All right. Centimeters over seconds, he says, and goes there is plus or minus. Okay. So there's our line equation there. Let's take a look at this. Seconds per centimeter. Thank you, sir. Have you ever heard any quantities that deal with distance over time or displacement? I mean, time over displacement? Because we got seconds over centimeters. Ever heard of any quantities like that? Okay, have you ever seen or heard of any quantities that have centimeters per second or something like it? Joe, yes. Nathan, yes. Keegan, yes. Keegan, what have you heard or experienced that has kind of the same type of units? Miles per hour, yeah. That's a distance or displacement over time. So this quantity right here with these units, we now use that as an operational definition. We're going to define that as velocity. So here is a definition to add to our list. We started last week. So velocity is change in position per unit time. Symbol for velocity is V. And it is a change in position over time. The reason we're going to drop the delta for our velocity equation is just about every single time we're going to start our time at 0. So the difference between when we stop our timing and where we started is just going to be what the clock reads. So these two we can equate to be the same thing, yes? Okay, so change in position. We said last week change in position is also the displacement that we see. So velocity can also be written as displacement per unit of time. So there are a couple of different ways we can write that velocity equation. So as Ben pointed out, in this graph, the slope of a position time graph is velocity. Major, important, you need to know it. Point. So the definition of velocity, important, need to know it. The fact that velocity is the slope of a position time graph, important, need to know it. High on your list of things to remember for the rest of the year. So if you had the hard job of collecting data this way, your life is easy from now on because you don't have to do anything except finish talking about the slope, talk about what you should have for y-intercept. Yes, ma'am? We've drawn the graph. You've written the line equation for each of your lines. You've told me what the slope means. You were assigned where to start for your position, so you should know whether you have a 0 y-intercept or not. If you should, what do you get to do? It's 5% check. So if you should have a 0 y-intercept, you need to do 5% check. All right? Time position graph. Is seconds per centimeter velocity? No. Okay, this is a quantity, new term. So the slope here, that quantity is called slowness. So slowness is the time per displacement, or the time per change in position. You ever dealt with slowness before? It's not as intuitive. It is not something that's in 99% of people's common experience. So it is less easy for us to work with a graph like this. So the slope of a time position graph is slowness. So for this graph, if time was your dependent variable, if position was your independent variable, you're going to do the same things. 2 line equations, one for each line. What does the slope mean? For your graph, the slope means slowness. You know whether you should have a 0 y-intercept or not because you were assigned where to start for position and where to start for time. If your vehicle started moving at time equals 0, then you should have a 0 y-intercept. If you were told to let it run, let time go by before you let the vehicle start moving, you're not going to have a 0 y-intercept. If you should have a 0 y-intercept, what do you get to do? 5% check again. In addition, if you have this graph, I'm going to ask you to generate a new one. So, for time position graphs, I want you to regraph it, and I want you to put position this time on the vertical axis. I want you to put time on the horizontal graphic. 2 lines again. So, if this was your graph, you're going to have two graphs in your lab notebook. When you regraph it and have position, vertical, time, horizontal, you do not have to do line equation, slope, etc. The only thing I want is this graph and to tell me why you needed to regraph it, and we'll talk about that in about 30 seconds. Those of you that had time independent, hands up. Time independent. Trevor, how easy was it to get your data?
Not